Welcome to the fourth part of Lesson 3. In this part of the lesson, we will look at a few of the properties and characteristics of alkynes, focusing on their structure and overall reactivity. Alkynes are an organic hydrocarbon that feature a carbon-carbon triple bond. The triple bond is comprised of a sigma bond plus two pi bonds. These two pi bonds are formed when the non-hybridized p orbitals, shown in red in the diagram below, overlap in a side-by-side orientation. This is possible because each carbon atom is sp hybridized. To understand this mode of hybridization, we can examine the atomic orbitals again for carbon, and consider that, to make an alkyne, we need a carbon that only bonds to two atoms at the same time. To make these two bonds, we need to use only two of the atomic orbitals in the hybridization process. By taking the 2s orbital and mathematically mixing it with one of the two p orbitals, we generate two new hybrid orbitals that are described as sp orbitals. These hybrid orbitals contain 50% s and 50% p character. Because we are only mixing in a single p orbital, which exists on one dimension of the Cartesian axis, that means our sp hybrid orbitals are also only in one dimension, along the same axis, 180 degrees apart. These two hybrid orbitals only allow carbon to form two bonds, specifically sigma bonds, as can be seen in the diagram showing bonding in acetylene below. The carbon-carbon sigma bond is formed by overlap of the sp hybrid orbitals present on each atom. The other bond, between the carbon atoms and the hydrogen atoms, is also a sigma bond, and is formed by overlap of a 1s orbital from the hydrogen atom and the other sp hybrid orbital on the carbon. This bonding description only accounts for two bonds at each carbon. We know that carbon needs to form four bonds in order to be in a normal stable state. This is where the p orbitals come in. Notice that when we made the two hybrid orbitals, we left behind two non-hybridized p orbitals. One is along the y-axis, and the other is 90 degrees away on the z-axis. These two p orbitals are shown in the diagram as the red and blue shaded lobes. When these p orbitals overlap with the p orbitals on the adjacent carbon atom, two pi bonds are formed. In summary, the alkyne triple bond consists of a sigma bond and two pi bonds. The sigma bond results from the end-to-end overlap of sp hybrid orbitals, and each pi bond results from the side-by-side overlap of two different p orbitals that are in orthogonal, that is 90-degree, planes from each other. Just like alkenes, alkynes can also undergo catalytic hydrogenation, resulting in their conversion from an alkyne to an alkane. The reaction requires the same conditions we saw earlier for catalytic hydrogenation, namely, that we treat our starting alkyne with hydrogen gas and a metal catalyst such as palladium on carbon. When performed in this way, two molecular equivalents of hydrogen are added across the alkyne triple bond, resulting in the complete reduction to the saturated alkane. Two examples of this reaction are shown below. Notice that in both cases, the hydrogenation works on both alkenes as well as alkynes. There is no selectivity to preferentially hydrogenating one instead of the other, with these conditions. The product of both reactions is simply an alkane. I suggest verifying that your starting material and product have the same number of carbon atoms. Do this by numbering the parent chain in both structures. Lindlar's catalyst is a modification to the catalyst used in the hydrogenation of alkynes. Lindlar's catalyst allows the chemist to selectively reduce an alkyne to an alkene, and stop, preventing any further reduction of the alkene to the alkane. The catalyst provides the ability to add only a single hydrogen molecule across the triple bond of the alkyne, and it won't add any hydrogen to an alkene. How does Lindlar's catalyst achieve this selectivity? Lindlar's catalyst is described as a so-called poisoned catalyst. What does poisoned mean in this context? It means that the catalyst has been modified to reduce its activity. Specifically, palladium, which is a highly active catalyst for hydrogenation reactions, is treated with lead acetate and quinoline, a nitrogen-containing heterocycle. This treatment makes the palladium less active, presumably by modifying the surface chemistry of the palladium metal, so it only coordinates effectively to alkynes and not to alkenes. Because the alkenes do not coordinate as well, they are not hydrogenated. Let's break this down step by step. Typically, if you take an alkyne and expose it to a regular palladium catalyst with hydrogen gas, you would completely hydrogenate the alkyne to an alkane. However, sometimes we want to stop at the alkene stage. This is where Lindlar's catalyst comes in. By using the poisoned palladium, we can selectively hydrogenate an alkyne to a cis-alkene. Cis, here, means that the hydrogen atoms add to the same side of the double bond, resulting in a cis-alkene. Here's a practical example. Imagine you have an alkyne, like 2-butyne, and you want to convert it to cis-2-butene. By using Lindlar's catalyst with hydrogen gas, you can achieve this transformation efficiently. To sum up, Lindlar's catalyst is a modified palladium catalyst that allows us to selectively hydrogenate alkynes to cis-alkenes. It's a very elegant solution for controlling the extent of hydrogenation in organic synthesis. A terminal alkyne is an alkyne with a triple bond at the end of the carbon chain. This means there's a hydrogen atom attached to one of the carbons of the triple bond. One of the most interesting and useful properties of terminal alkynes is the acidity of their terminal hydrogen atom. Terminal alkynes, which have a pKa of 25, are significantly more acidic than alkenes and alkanes, which have pK values of 45 and 50 respectively. The hydrogen attached to the carbon in a terminal alkyne can be removed by a strong base, forming an acetylide anion, which is the name used to describe the conjugate base of a terminal alkyne. The relative acidity comes from the sp hybridization of the carbon atom in the triple bond. The sp hybridized carbon is much more electronegative compared to sp2 or sp3 hybridized carbons. This higher electronegativity allows the carbon to hold the negative charge of the conjugate base, the acetylide anion, making it more stable. To deprotonate a terminal alkyne, we use a very strong base, such as sodium amide, whose formula is written as NaNH2, or an organolithium reagent, like N-butyl lithium. What is the value of the acetylide anion? The acetylide ion is a strong nucleophile, which means it can donate a pair of electrons to an electrophile to form a new bond. This property is particularly useful in forming carbon-carbon bonds, which is a key requirement for building complex organic molecules. To summarize, terminal alkynes are relatively acidic due to their sp hybridized carbon, allowing them to be deprotonated by strong bases to form acetylide ions. These acetylide ions are excellent nucleophiles that can participate in carbon-carbon bond-forming reactions, significantly expanding the versatility and complexity of organic synthesis. That concludes Lesson 3. Congratulations! I hope you have enjoyed learning about alkenes and their reactions, and now have a greater appreciation for what organic chemistry is all about. We have covered a lot of ground in this lesson, and I am pleased you have made it this far. In the next lesson we will open up a new chapter in organic chemistry, specifically one that deals with the fascinating world of the so-called aromatic compounds, a class of substances with a rich history of mystery and intrigue. I look forward to seeing you in the next lesson. Bye for now.